Okie dokie. Let's get started. Hold on a sec. All right, so what are we going to talk about today? We're going to jump into eigenvalues and eigenvectors. I have some announcements at the end. I think once more people come in, that's when the announcements are going to be more relevant. So let's just jump right in then to material for today. We're going to start off talking about change of basis. And like, there are more people at the snow day recitation than there are right now. That's not a good sign. Anyways, change of basis. All right, so there's really one type of change of basis that I really want to talk about. So in chapter 7, we care about the following. Okay, so in chapter 7, we care about the following change of basis. Let B equal the standard basis for V. And V is an n-dimensional vector space. Okay, and then let C equal just some vectors V1, V2, all the way through Vn, which is another basis for V. Make sure I'm recording. Okay, yeah, we're good. Okay, so I have your so B is the standard basis, and C is just any other basis for V. So what I care about then is the following. What is P from C to B? Okay, and so how do we set this up? Well, P from C to B, right? Set up your augmented matrix. C is on the left-hand side, B is on the right-hand side. Okay, but what go in the columns of the B matrix? Well, you have just your standard basis. And what happens when you put your standard basis on the side of a matrix? Okay, but what is B, right? Since B is the identity matrix, right? Because your standard basis is always like 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, right? 0, 0. So B is just going to be the identity matrix. All right. And C is just going to be whatever vectors you have, right? V1, V2, all the way through Vn, put in column form. But then what is your change of basis matrix? It's just C, right? Because you're already done, right? You already have the identity matrix on the left. So yeah, so when B is the standard basis matrix, this is just going to be P from C to B, right? There's no work you need to do. It's literally just the basis vectors of C all written down. Okay? All right, now a similar question is, what is P from B to C? All right. Well, we learned previously that if you go from one change of basis to the other, then the reverse direction is just an inverse, right? So P from B to C is just equal to P from C to B inverted. Okay, and so P from C to B is going to be equal to V1, V2, all the way through Vn, right, in the columns. But we're just going to invert this matrix because we want it going the other direction. Okay? Are we okay with these two change of basis matrices? And these are the two that we really care about, as we'll see in a little bit. Okay. If no questions, let's jump right into the main material of the day. Eigenvalues and eigenvectors. So what are eigenvalues, eigenvectors? They're the following. If a linear transformation, let's call T, has a square matrix representation, so an by n is the matrix that represents T, and it's going to be a square matrix. All right. What are the eigenvalues and what are the eigenvectors? Well, the eigenvalues, okay, let's start with eigenvectors. Sorry. The eigenvectors are going to be the inputs that are stretched by the map, and the eigenvalues are going to be how much the eigenvectors are stretched. Okay, so the eigenvectors, so they're going to be stretched by the map. Eigenvalues tell you how much they're stretched. So a visual example then in three-dimensional space is on your previous homework that you just turned in this week for recitation, and it'll be on your homework for next week as well. So this is more or less kind of like an answer to a problem. But if you think about it, let's think about reflections in three-dimensional space, right? You have a plane. Right? And you have your eigenvectors. You have your eigenvectors. Well, you have vectors that are getting reflected by the plane, right? So let's think which vectors then have their direction, or which vectors are just simply stretched by a reflection. Okay, yeah, so the perpendicular one is going to get stretched by the reflection, right? Because if my pen is the eigenvector, it just gets flipped to the other side, right? But how much does it get stretched by? -1, right? So the eigenvalue associated with that would be -1. All right. What are my other eigenvectors? Well, they're the ones lying on the plane, right? Because if they're lying on the plane and I reflect them over the plane, they're still going to be lying on the plane, right? So what is then the eigenvalue associated with the eigenvectors that are lying on the plane? 1, right? Because nothing happens to them, right? So that's kind of the geometric then idea behind your eigenvalues and eigenvectors, okay? In terms of a reflection. Okay, so that's going to be reflection for eigenvalues and eigenvectors. More formally, here's the definition. All right, the definition of eigenvalues and eigenvectors is going to be the following. AV is equal to lambda V. All right, and this is a very important definition because anything that we make you prove about eigenvalues and eigenvectors most likely will be using this definition in some sort of way. Okay, another way we can write it is we can subtract lambda V from both sides, so then we'll get AV minus lambda V. All right, and then we can factor out a V, but we have to remember it's vector multiplication, so that's also equal to A minus lambda I times V. All right, where I is the identity matrix. All right, so these three, like this definition right here and this definition right here, so A minus lambda IV is equal to 0. That's another definition, and then this is one of the definitions. Those are going to be the two that you see the most often. Okay, and in this case, V is your eigenvector, and lambda is your eigenvalue. Okay, and let's see this definition at work. So, for example, prove that if lambda is an eigenvalue for A, then lambda squared is an eigenvalue for A squared. Okay? So if lambda is an eigenvalue for a, you want to show that lambda squared is an eigenvalue for a squared. And given that I gave you the definition up there, which is av equals lambda v, we probably want to use that, right? So what do we know? Okay, we know that lambda is an eigenvalue for a. Okay, so since lambda equals an eigenvalue for a, it means that we know that there's some av which is equal to lambda v, right? So we can use that as a fact. All right, but what do we want to show? We want to show that a squared times v is equal to some lambda squared times v, right? We want to show that lambda squared is an eigenvalue for a squared. So we're not sure if this is true. Okay, and how do we go about showing that this is true? Well, we always, when you have something like this, you generally want to start off with what you want to show, or one side of the equation of what you want to show. All right? And in this case, we're going to start off with the left side of the equation. All right? So let's start off with a squared v. All right? So we want to eventually get to lambda squared v, right? But we have to take a series of steps that make logical sense to get there. So what is a squared v equal to? And remember, we want to leverage av equals lambda v somehow. So what is a squared? A times a, right? So if I write it out that way, a squared v is equal to a times av. Okay? So now we have an av right there. But what is a times v? Lambda v, right? We know that from our fact. So this is a times lambda v. All right, what is lambda? Lambda is an eigenvalue, it's just a scalar, right? So I can pull out the lambda in front. So this is now lambda times AV. But what is AV? Lambda V. Right, so now I got lambda times lambda V, which is equal to lambda squared V. Okay? So now we've shown that a squared V is equal to lambda squared V, and therefore lambda squared is an eigenvalue for a squared. All right? Do you see how we're supposed to play around with this definition? You'll have some things to try. All right, homework. Okay, any questions? All right. So that's an example about using the definition. There are two important facts about eigenvalues. The first one is that the product of your eigenvalues is equal to the determinant of the matrix A. And the second one is that the sum of the eigenvalues is equal to the trace of the matrix A. All right, and you should use these two to your advantage when computing eigenvalues and eigenvectors. All right, and I can't stress how useful this is. There are going to be some matrices where it seems impossible to compute eigenvalues and eigenvectors, but you can leverage this fact, these two facts, to like effortlessly find what your eigenvalues are. And I can't, like, it's really important you know how to use these and when to use these. Okay? So I think there's one problem on the actual homework that's coming up where it's a bunch of repeated numbers. You should use these two facts to your case to help you there. Okay. So let's just talk about finding eigenvalues and eigenvectors. I'm just going to label it finding eigen. So this is an easy example. And we'll actually get to one where that's like very computationally tedious in a little bit. So here it is. 2, 0, 0, 1, 3, negative 2, 1, 4, negative 3. All right. Step 1 is to find the characteristic polynomial. All right, so this is a vocab term that you should know. And what is the characteristic polynomial? It's the determinant of a minus lambda I is equal to 0. All right, so what is determinant of a minus lambda I? Well, I is the identity matrix. Lambda I is just lambda on the diagonal, right? So then a minus lambda on the diagonal is literally you just take lambda off the diagonal of a, right? So you want to find the determinant of 2 minus lambda, 0, 0, 1, 3 minus lambda, negative 2, 1, 4, negative 3 minus lambda. Okay, so that's the determinant of the matrix we want to find. How are we going to do this? Cofactor expansion. So here's the thing for eigenvalues and eigenvectors. Don't use row reduction, because how do you cancel out the 1 with 2 minus lambda? All right, the answer is you're not going to. So the only way really to compute these is using cofactor expansion. So in this case, it's easy because there's only one cofactor expansion to do, which is 2 minus lambda, right? And then times the determinant of the lower right cofactor. So that's 3 minus lambda, negative 2, 4, negative 3 minus lambda. Okay, what is that equal to? That is equal to 2 minus lambda times 3 minus lambda, negative 3 minus lambda, plus 8, right? Because if you go 4 times negative 2, that's negative 8, but you're subtracting it. So this is 2 minus lambda, lambda squared, minus 3 lambda, plus 3 lambda, minus 9, plus 8. All right, and now this is 2 minus lambda, and this simplifies to lambda squared minus 1, which we know how to factor. That's 2 minus lambda, lambda plus 1, lambda minus 1. And remember, this is all equal to 0, since we're supposed to set the determinant of that equal to 0. Okay, so now our eigenvalues are the roots to this polynomial, which are negative 1, 1, 2. So I'm just going to write it in descending order. It doesn't matter. Any questions about finding the characteristic polynomial and the eigenvalues? Okay, here's the thing. If you don't get this right on the exam, this is how I grade this problem. I give you 3 out of 10. I don't look at the rest of your work. All right. Find the right characteristic polynomial, because otherwise everything else you do is meaningless. All right. And how do you know that you're even somewhat within the correct ballpark, right? So first of all, calculation of the midterm, they'll turn out to have nice eigenvalues. You're usually not going to have an eigenvalue of 175 over 17. All right, that's not going to be an eigenvalue. They're going to be usually integer numbers. All right, and the other thing is, remember the fact up here, the sum of your eigenvalues is equal to the trace. So what's the trace of A? It's 2, right? It's 2 plus 3 plus negative 3, right? Trace is the sum of the diagonal entries. All right, so the trace is 2. What is the sum of your eigenvalues here? It's 2 plus 1 plus negative 1. It's also 2, right? So you do have methods to check yourself to see if you're getting the right eigenvalues, all right? Get the right eigenvalues, because you're not going to get a lot of points on the exam if you get the wrong eigenvalues. All right, so, all right, that ran over. Let's move on. Step 2, after you get the eigenvalues, is you want to inspect. All right, so for every lambda, inspect the kernel of A minus lambda I to find eigenvectors. All right, so once we have each lambda, we have to plug in that lambda into A minus lambda I, and then we look at the kernel of the resulting matrix. So it probably makes more sense after I do this. So let's take lambda equals 2, right? That's my first eigenvalue. All right, so what is A minus 2I? Well, you go back to your original matrix, right? And you just take 2 off the diagonal. So you'll have 0, 0, 0. Right, 1, and then this was 3, so 3 minus 2, that's 1. Negative 2, 1, 4, and then this was negative 3, so now you get negative 3 minus 2, it's negative 5. Okay, so now what do you want to look at? You want to look at the rank of this matrix, which is what? It's 2. All right, it's not in row echelon form, but if it were in row echelon form, you'd have 2 rows that are non-zero. Okay, and then more importantly, we care about the nullity, which is what? One, by the rank nullity theorem. Okay, so in my kernel then, it's going to be a span of how many vectors? 1 vector. All right, and so remember on last week's recitation homework, we asked you to eyeball vectors in the kernel. This is why. All right, this is where we're going to use it. So what's a vector that's in the kernel of A minus 2I up there? Not 1, 0, 0. 1, 1, 1. Someone said it, right? So 1, 1, 1 is a vector in the kernel, right? And so why is 1, 1, 1 in the kernel? Well, this is just the work to show it, right? If you multiply by 1, 1, 1, right? 0 plus 0 plus 0 is 0. 1 plus 1 minus 2 is 0. 1 plus 4 minus 5 is 0. Okay? So the kernel is going to be the span of 1, 1, 1. All right, so this is essentially your first eigenvector. So this is like v1. Okay, lambda equals 1. Right, now you got A minus I. What is that equal to? You get, right, 1, 0, 0, 1, 2, negative 2, 1, 4, negative 4. Okay, what's the rank? It's 2. Double the second column minus the first. Double the second row minus the first row, and you'll get row 3. Okay, so that ranks 2. Nullity is 1. Nullity is equal to 1. So the kernel is equal to the span of what vector? 0, 1, 1. Okay, and then lambda equals negative 1. Remember, it's A minus lambda I, so now this becomes A plus I. 3, 0, 0, 1, 4, negative 2, and 1, 4, negative 2. Okay, the last row is pretty clearly the same as row 2, so the rank is 2, which means that the nullity is 1. So what's the kernel? 0, 1, 2 is in the kernel. Okay. So again, how do we eyeball? Essentially, you just go term by term, and you're like, okay, what works? Something times 3 plus something times plus 0 times something plus 0 times something has to get me 0, right? So I know this first term has to be 0, since it's 3 times 0. And then you work it out between 4 and negative 2, and you look at 4 times 1 and negative 2 times 2, and that's how you figure out a vector in the kernel. Okay? So this really just more practice will get you the answers. Okay, so this is like v2, this is v3, and so we say that v1, v2, v3 form an eigenbasis for the eigenspace of the matrix A. All right, so the 3 eigenvectors that we found, they're going to be linearly independent from each other. Linearly independent from each other, okay? v1, v2, v3, they're linearly independent. They span R3, so they are going to form an eigenbasis for the eigenspace of A. Okay? You can also have the eigenspace for the lambda value, and that's just the associated eigenvector. All right? So there's a lambda space for the entire matrix, which is all of the eigenvectors, and then there's an eigenspace for just the eigenvalue, and that's just the eigenvectors that you found using that eigenvalue. Okay? So there's a distinction there. It's pretty subtle. Keep that in mind. Okay. Any questions on this? So this is how you find eigenvalues, eigenvectors. All right. So now let's talk about multiplicity. So everything from here on out is going to be new. All right. I don't think you've really talked about this in class yet. So it's going to be looking at what we're going to do tomorrow. All right. There are a few terms here. There's the algebraic multiplicity. Of lambda. So for some eigenvalue, right, it has an algebraic multiplicity. And what it is, it's the number of times lambda shows up in the characteristic polynomial. Okay, so above, right, we had 2, 1, negative 1. That means the algebraic multiplicity for 2 is 1, right? 2 shows up once. And the algebraic multiplicity for 1 is also 1, because it shows up once, right? If you have repeated eigenvalues, that's when the algebraic multiplicity is not just 1. Okay? And we'll see an example a little later on. There's geometric multiplicity of lambda, which is the dimension of the kernel of A minus lambda I. Okay? So what we had up here, right? So for example, for lambda equals negative 1, right? The algebraic multiplicity was 1, and the geometric multiplicity was also 1. Okay? So they were equal to each other. That's not always the case. So the general form is that algebraic multiplicity is going to be greater than or equal to the geometric multiplicity. All right? If algebraic multiplicity is equal to 1, then geometric multiplicity must be 1. Why is that the case? So what other value could the geometric multiplicity be if the algebraic multiplicity was 1? It'd be 0, right? It's the only number less than or equal to 1. Well, okay, you can't have negative multiplicity, so let's just take that for granted, right? So what if the geometric multiplicity was 0? Is there an eigenvector we can find for that eigenvalue? No, right? Because how do we find eigenvectors? We looked at the nullity of A minus lambda I, right? We looked at the nullity, we looked at the kernel of a minus lambda I. So if the geometric multiplicity is 0, what's the only vector inside the kernel? The 0 vector, all right? And don't put the 0 vector down as an eigenvector. We're just not going to give you points for that problem. Okay? The 0 vector is never an eigenvector. So if you have geometric multiplicity equals 0, guess what? You found the wrong eigenvalue. All right? So you shouldn't ever have geometric multiplicity 0 for an eigenvalue. All right. So that's if algebraic multiplicity is equal to 1. That forces geometric multiplicity to be 1. If this relationship is strictly greater, right? If algebraic multiplicity is greater than geometric multiplicity, bad things happen, and we'll save that for after break. All right. So for today, don't worry about it. You don't have to worry about it on the homework up until next week. But once you do have to start worrying about it, the computations get really bad, like really bad. So for now, it's okay. All right. So now that we have algebraic multiplicity and geometric multiplicity, let's talk about diagonalizability or diagonalizable. All right. So what's the definition of diagonalizable? All right. We say that a matrix A is diagonalizable, and I just abbreviated diagonal, right? I don't think there's any other word that uses these letters. Matrix A is diagonal if we can write A is equal to SDS inverse. Okay? S is going to be a matrix of eigenvectors. You can think of it as your eigenbasis matrix. D is a diagonal matrix with your eigenvalues. On the diagonal. Okay? Yeah.
When you make these matrices, does it matter what orders you put the vectors in?
We'll get to it. It actually doesn't. So essentially, they have to correspond to how you put your eigenvalues in the D matrix. But we'll get to that when we do the example. So for now, just don't worry about like what order you put it in. Okay, so that's the definition of diagonalizable. All right, is if we can write it in that form. And what's the condition? The condition for it to be diagonalizable, A is diagonalizable if every unique lambda or every unique eigenvalue has algebraic multiplicity equal to the geometric multiplicity. All right. So if the algebraic multiplicity of an eigenvalue, of every eigenvalue of that matrix is equal to the geometric multiplicity, we can write it as SDS inverse. All right? Which is why I said bad things happen if they're not equal to each other, because first of all, it's not diagonalizable, and so that just creates a lot of problems. All right, so this is the condition that is required. All right, every unique lambda has algebraic multiplicity equal to geometric multiplicity. All right, let's take a look at an example. All right, and I think most of this example will be spent calculating the darn characteristic polynomial. A is equal to negative 4, 3, 3, negative 3, 2, 3, negative 3, 3, 2. All right, so how do we diagonalize a matrix? Step one is always find the eigenvalues and eigenvectors. Okay? From here on out, if you see a square matrix and you have no idea what to do in the problem, find the eigenvalues and eigenvectors. You're probably doing the right thing. All right, so find the eigen stuff. All right, and step two is write it in SDS inverse form, if possible. Okay, so let's find the eigenvalues and eigenvectors. This is a massive pain in the ass to find for this matrix. Determinant of a minus lambda I is equal to the determinant of negative 4 minus lambda, 3, 3, negative 3, 2 minus lambda, 3, negative 3, 3, 2 minus lambda. All right, unfortunately, we can't just cofactor expand one value. We have to cofactor expand along entire row or entire column. There's no good way to do this problem, so I'm just going to cofactor expand along the first row. Hope for the best. All right, so what is this? This is negative 4 minus lambda, all right, times the determinant 2 minus lambda, 3, 3, 2 minus lambda, minus, all right, remember the second term is always a minus, 3, this is like your standard cross product stuff here, or you can use the negative 1 raised to the power. Negative 3, 3, negative 3, 2 minus lambda, and then plus 3 times negative 3, 2 minus lambda, negative 3, 3. So on your midterm, it probably won't be this bad. All right, we'll try to avoid giving you a characteristic polynomial. That will take ages to find. This is essentially like my tax on myself for like, I need to do one of these calculations for you guys at some point. So this is it. Okay, what happens, well, this is negative 4 minus lambda. The determinant of this matrix is 2 minus lambda squared minus 9. All right, minus 3 times, and the determinant of that is negative 3 times 2 minus lambda plus 9. All right, and then this last one is plus 3, and then this determinant here is negative 9 plus 3 times 2 minus lambda. All right, there's a few things you can do from here. You can FOIL everything, get a cubic polynomial, and factor the cubic polynomial. All right, that's a legitimate option. We're not going to go over how to factor cubic polynomials. Last semester in lecture, they spent like 40 minutes going over it, and a lot of people thought it was a massive waste of time, and I agree. So learn how to factor cubic polynomials on your own. If you don't know how to factor cubic polynomials, like me, you can just play around with this expression until you get a linear term and a quadratic term. All right, and so that's what we're going to do here. So what's going to happen, okay, so first I'm going to distribute. Right, so let's distribute. So what do I mean? So this is like negative 4 minus lambda times 2 minus lambda squared minus negative 4 minus lambda times negative 9. Or, okay, so minus 9 times 4 minus lambda. That's the better way to do it. Okay, and then distribute this 3. This is plus 9 times 2 minus lambda minus 27. And then distribute this 3 again. This is minus 27 plus 9 times 2 minus lambda. Okay, what's the next step? I'm going to group the 2 minus lambda terms. I'm going to factor out a 2 minus lambda. So this term, and this term, I'm going to group. I'm going to factor it out. All right, so this is 2 minus lambda times, all right, negative 4 minus lambda. And then since this was 2 minus lambda squared, there's still a 2 minus lambda term remaining. All right, you factor out a 2 minus lambda out of 9 times 2 minus lambda. That's just plus 9. And then you factor out a 2 minus lambda from the other term there. It's also a plus 9. All right, so it's 2 minus lambda times all of that. Okay, and then everything else, you just write it out. So this is negative 9 times negative 4 minus lambda. And then you got negative 27 minus 27, so that's minus 54. Okay, so now what do? We FOIL everything on the inside. So this is 2 minus lambda. This becomes lambda squared plus 2 lambda minus 8 plus 18. All right, and out here this becomes plus 36 plus 9 lambda minus 54. Okay, so now this is 2 minus lambda, lambda squared plus 2 lambda plus 10 plus 9 lambda minus 18. All right, so 36 minus 54 is negative 18. And then I simplify the inside. Okay, but I can factor out a 2 minus lambda out of 9 lambda minus 18. All right, and how do I do that? Well, this is negative 9 times 2 minus lambda. All right, so now what do? Then out of all of this, I factor out another 2 minus lambda. So now I get 2 minus lambda times lambda squared plus 2 lambda plus 10. And now, since I factor out another 2 minus lambda, that's a minus 9. So I get lambda squared plus 2 lambda plus 1. And we have our linear term. We have a quadratic term that we actually know how to factor. 2 minus lambda, lambda plus 1 squared. Okay, so just a lot of algebra. It's nothing you can do. All right, so now what? Now, okay, so lambda is equal to 2, negative 1, and negative 1, right? So negative 1 appears twice, and the way I write it usually is is 2 and then negative 1, and I say mult 2. And when I mean mult here, I mean the algebraic multiplicity. Okay, so now let's find the eigenvectors. Lambda equals 2. A minus 2i is negative 633, negative 303, negative 330. Okay, so what did I say about? So what's the what's the algebraic multiplicity of 2? It's 1, right? Because it only shows up once. Okay? So if the algebraic multiplicity is 1, what does the geometric multiplicity have to be? 1. It has to be 1, right? Which means that the nullity is 1. So the nullity of this matrix is 1. All right? Which means the kernel is the span of something what's an eigenvector? Yeah, 1, 1, 1. Okay. Kernel span 1, 1, 1. Okay, we're done. The nullity is 1. There's only one eigenvector there. All right. So now lambda equals negative 1. Right. Keep in mind this is algebraic multiplicity. It's equal to 2. So now I got a plus I, and since the algebraic multiplicity isn't 1. I actually have to calculate the rank and the nullity of this matrix. Well, the matrix ends up just being the same thing repeated in 3 rows. Which is nice, because what is the rank of this matrix? Yeah, it's 1. So what's the nullity? It's 2. Well, that's great, right? Because the nullity is the geometric multiplicity. Right? So if nullity is 2 and it's the geometric multiplicity and here's the algebraic multiplicity, well, they're equal to each other. So that means our matrix is diagonalizable because we've shown for every unique eigenvalue, the algebraic multiplicity is equal to the geometric multiplicity. All right? So we're good. So that means the kernel is going to be the span of how many vectors? two vectors, and can someone give me one of them? 1, 1, 0. 1, 0, 1. Okay? Any questions about finding the eigenvalues, eigenvectors here? All right, so now what's the next step? So A is diagonalizable, which means A is equal to SDS inverse. So that's here's S, here's D, here's S inverse. Okay, so how do we actually find what S and D are? So that's going to be the most important thing. So for D, it's really simple. Just put the eigenvalues on the diagonal. All right, doesn't matter what order they're in. You can just put it in whatever. Generally, try to keep the repeated ones next to each other. It's a good habit to do that. So in my case, I'll just do 2, -1, -1. Okay, so the eigenvalues go on the diagonal for D. So now what is S? Well, since the first column of D has 2 in it, the first column of S needs to have the eigenvector that goes with 2. All right, so what's the eigenvector that corresponds to lambda equals 2? Well, if we scroll up, 1, 1, 1, right? So this column has to be 1, 1, 1. All right. Now you have -1 and -1, and how many eigenvectors did we have for -1? Well, we had 2 of them, right? So in this case, it doesn't matter which way you put them in. You just got to make sure that they're associated with the right eigenvalue. So if these are 1, then this one, let's just put 1, 1, 0, and here let's put 1, 0, 1. It doesn't matter. You can flip them. Okay? And then the same thing, well, S inverse is just S, so 1, 1, 1, 1, 1, 0, 1, 0, 1, inverted, right? So let's just not calculate what that is for now. It's fine. Okay, so this is how you write down the matrix in diagonal form. Any questions? Okay, so for those who walked in late, you missed the beginning. But what we talked about is a certain change of basis matrix, right? Where if B is the standard basis and C is some other bases, right? We can find PCB and we can find PBC, right? So if B is the standard basis and you're trying to go from C to B, your change of basis matrix is literally just the basis vectors in a matrix, all right? And then if you want to go the other direction, if you want to go from the standard basis to basis C, it's just the inverse of your basis vectors, right? So does this look familiar? Well, it's essentially what diagonalizing a matrix is doing, right? So what's going on? Well, if you go all the way down, right? If we let B be the standard basis, and so B is the standard basis, and C is the eigenbasis. Right? What is S inverse? Well, S inverse is going from the standard basis to the eigenbasis. Right? So this is P from B to C. Right? And if you compare, so this is recorded, but if you compare what I did at the beginning to right now, that's the exact same matrix, right? I just put the basis vectors in a matrix and I inverted it. All right? What is this? It's a diagonal map, right? So this is step 1. This is a change of basis to the eigenbasis. Damn it. Right? So the first thing that happens is that you change the basis to an eigenbasis. The second thing that happens is this is a diagonal map. This is like TCC. All right, it's the map with respect to the eigenbasis. and it's a diagonal map. Apply the diagonal map with respect to the eigenbasis, which is C. All right, this is step 3 right here. What is this? This is the change of basis matrix from your eigenbasis back to the original basis, right? So this is P from C to B. All right, and so this is a change of basis back to the standard basis, right? And all of this is equal to A, and A is really the same thing as like TBB, right? So what we're really doing with the diagonal matrix, with diagonalization, is that we have some matrix A, which is a map, right, which is a linear map, and we can write it so that it's really just the application of a diagonal map. So this is actually really helpful for like computers to use, right? Because with matrix multiplication, you run into like a lot of computations when you're just like taking dot products repeatedly. But if you take just a diagonal map, you have really few computations to take, right? So that's why diagonalization is so useful. Another reason diagonalization is so useful is, does this look familiar? Right? What did we do on homework that we used something like this form? Exponents, right? Yeah, so if you have A to the n, that's equal to S d to the n S inverse. Right? Remember, we showed this on homework. So it's really useful to use diagonalization in finding exponents of matrices. Okay, and then, yeah, so I'm going to stop here. A few announcements. I do have homework 4 and homework 5 graded, even though they're muted on Canvas. What's been happening is, well, so from my observation is that the homework quality is kind of going down. So for homework 5, I graded like 45 homeworks, and I gave 4 perfect scores. So I understand the material is getting harder, which like is like the imperative that like you need to start the homework a little earlier, because like I have Friday office hours, and Nibby has Friday's office hours, and we get about 0 people at those office hours. Whereas on Monday, it's like we have to fill up 2 classrooms. So keep that in mind. All right. Another thing. This recitation homework is long. All right. It's really long. It's 2-sided too. It's due after spring break. It's going to be worth 2 recitation homeworks. One of the sides is just true false with no justification. So if you're really running out of time, you can just go through and just put true on everything. It doesn't matter, okay? We're only grading like the true false there. The other side are like previous exam problems from stuff from this section. And you should be able to do all of these. So what I'm going to do is that because this is a pretty difficult recitation homework, I'll probably be holding some kind of office hours over spring break, which is like some kind of like Skype or like Google Hangouts type of office hours, where you can just like call in or like just like chat in with your questions. Get started early. You're not going to finish this the night before. I guarantee it, okay? So, all right, let me hand these out. The recitation's recorded. There are a few other notes on top of the recitation homework. So I always have like my preparation notes. Actually, let's just hand this. So I always have my prepared notes for recitation. There might be a few other things on there, especially at the end, that might be helpful for homework, but I'm not that I didn't get to it. Yeah.